Hi, my name is Alex Fleischman, and welcome to the video overview for the Newton's Cradle demonstration. This demonstration will allow students to observe how momentum is conserved using a Newton's cradle. Students will observe how one raised Newton ball can transfer its momentum through multiple Newton balls. Let's review some principles. First, momentum is equal to mass times velocity. Next, momentum is conserved in a closed system. Therefore, initial momentum is equal to final momentum. Next, impulse. Impulse is the product of a force exerted on a system and the time for which the force is exerted on the system. Therefore, impulse is equal to force times delta t, with delta t being the change in time. In an open system, we could state that initial momentum plus impulse is equal to final momentum. Therefore, initial momentum plus force times delta t is equal to final momentum. Let's review the difference between closed systems and open systems. A closed system is a system in which energy or mass cannot be lost to or gained from the environment. An open system is the opposite of a closed system, so energy or mass can be lost or gained from the environment. So let's work through this demonstration. First, raise one Newton ball from a set height. Allow a system to return to rest. Now raise two Newton balls from a set height and allow the system to return to rest.
Cool. Thanks, Newton. My main man.
Let's go through some questions. What caused the final ball to move? Well, the momentum from the first ball is transferred through each of the other Newton balls until it reaches the last ball, which rises into the air. What causes the system to return to rest? Well, the force of gravity is exerting an impulse on the system over the time the system is in motion. This eventually causes the ball to return to rest. Let's work through a simple problem. Suppose we have a Newton's cradle with 5 Newton balls. The Newton balls are 0.13 meters above the table when at rest. One ball is lifted to a height of 0.24 meters above the table and is released. Assume this takes place in a closed system. Calculate the velocity of the first Newton ball just before it collides with the second Newton ball. Well, we have to use the conservation of energy. When the ball is initially released, it only has potential energy. When the ball is just about to hit the second Newton ball, it has both kinetic and potential energy. Therefore, we could state that mg h raised plus h to the table is equal to 1/2 mv squared plus mg h to the table. First, we can divide both sides by m. Then multiply both sides by 2 to get rid of the 1/2. Then we could bring the 2g h to the table to the opposite side of the equation. Then we could take the square root of both sides. Then we can note that all the heights are multiplied by 2g, so we could take the 2g to the outside. Then we can note there are two h tables, so we could cross the two h tables out, and just get v is the square root of 2g h raised. And that means that the velocity right before the ball collides is equal to 2.17 meters per second. Next, using the same information, calculate the velocity of the last Newton ball before it begins rising. Well, it's stated in the problem that it's a closed system, therefore initial momentum is equal to final momentum. Noting that each balls have mass m, we could state that mv of ball 1 is equal to mv of ball 2. Then we could divide m by both sides and get that the velocity of ball 1 is equal to the velocity of ball 2, therefore the final ball has a velocity of 2.17 meters per second. Part C. Calculate the maximum height of the last Newton ball after the collision. Well, initially, the ball has both kinetic and potential energy, but when it reaches its maximum height, it only has potential energy. At this moment, pause the video and look through the derivation for the maximum height of the final ball, and note that the final height is 0.24 meters. Let's make some conclusions. The initial height of the first Newton ball was h raised, and that's equal to the final height of the last Newton ball, which is also equal to h raised. This phenomena occurs only in a closed system, due to no external work being done on the system to affect the conservation of energy, and no net impulse to affect the conservation of momentum. So realistically, why does the Newton balls in our experiment return to rest? This is because energy is lost in the system. Energy could be lost from a frictional force of the Newton ball strings rubbing against the support beams, the heating of the spheres due to the collisions, or even the spheres not moving in a perfectly straight line.